What we do with these dragons is we have, it's a monohybrid cross, so it's very easy. So we have dominant scaly and recessive smooth skin. Okay? And you have done that in the BI308, I think, in the genetics stuff. So it shouldn't be terribly difficult for you to set up a Punnett square when you cross two heterozygote dragons. Okay, so very simple, you can do that. Just very quickly fill in this form. And now, so you've done it. Okay, good. And now we count our offspring. Now, it is very well-known fact that this particular kind of dragon is very prolific. So we have a total of 40 offspring. And hopefully then next term, you will be immediately able to tell me what kind of strategist this dragon is, whether it is a K or an N strategist. And as a biologist, then you will also be able to tell me which ecological niche this dragon is occupying, just by looking at the numbers. You look terrified.
No, it should have been R strategies because they
or K and R, yeah.
Because they produce so prolific.
Yep. Well. Okay, so what we find is that I give you some numbers now. We have 3, we have 12, we have 13, and we have 12. Right? So these are our numbers that we observe. Now, one thing that I want to point out is I've left some of these grids empty, because that is something that we occasionally need to calculate. So this row here, or this, so I should say this column here, this is called the marginal rows. And this one here is called the marginal columns. Marginal because it is in the margin of this table. And what it just simply does is it counts what's in the row and the column respectively. So here the marginal rows, 3 at 12 gives me 15. Yeah? This one gives me 13 at 12 gives me 25. And hopefully everything adds up to 40. This is the grand total. And you can do a check with the marginal columns. So this gives me 16. This is this and this. And 12 and 12 gives me 24. And yoo-hoo, it is 40. Also the grand total. Now, when we look at our dragons, we want to know whether this is a Mendelian inheritance. Right? So we look at the phenotype. And we know that scaly is dominant over smooth. So, what would be the Mendelian monohybrid dominant ratio? It would be 3:1, wouldn't it? For a monohybrid.
If you're looking at normal,
Sorry?
if you're looking at normal monohybrid.
At a normal monohybrid, it would be 3:1. Okay. So, does our phenotype, well, our Punnett square, does this confirm our phenotype? And that is exactly what we can actually investigate with our chi-square test. So what we can do is we can do exactly the same thing for expected numbers, and I do that in red. What would we expect for each of these squares if it was just simply by random, the numbers? We would expect for each square 10, 10, 10, and 10, right? Because it's absolutely random. This is what our expected numbers would be. Again, we have 4 times 10, so we have our 40 little baby dragons. Now, for the goodness of fit test, we said we look at the phenotype, and we basically have 2 phenotypes. We have the scaly and we have the smooth. And we would expect a 3:1 or expected 30:10 distribution. Yeah? Now if we look at our actual numbers, which one are scaly? This one would be scaly. What about this one here? Scaly? Scaly, because it's S, capital S and lower. What about this one here? Scaly? Scaly. What about this one? That's smooth. Okay, so we have 3 at 12 is 15, at 13 is 18 scalies, and 12 smooth. What did I say?
18.
28. Observed. 28 scalies and 12 smooth. Okay? Goodness of fit. So we can use this program that I showed you, for which I haven't given you the link, which I realize, but I will send it out tonight. So we do the goodness of fit. And we get a p-value for this. P-value equals 0.485, and our alpha for that is 0.05. Is there a statistically significant difference between the observed and the expected data?
Because p-value is high, so we can sort of...
So P is high.
So the null hypothesis.
The null hypothesis in this case, the null hypothesis is there is no significant difference. So H null can stay. So there is no significant difference. Our numbers that we get here for the phenotype support our 3-to-1 ratio. So that indicates that there is a true monohybrid split between the phenotypes. That is what our calculation says. Yeah? Does that make sense? So true monohybrid. True monohybrid phenotype. Okay, so far, so good. Bing. Okay. Now, what about, well, let me go back to that. What about the genotype?
For that last question, what was the null hypothesis?
The null hypothesis is always, null means no difference. No difference between observed and expected. Yeah? That's for the chi-square test. What about the genotype? What would be, I just simply write down the same grid again. Three, 12, 13, 12. And it should give 40 again. What about the genotype? What do we expect?
We expect a 2-to-1 ratio.
Sorry?
A 2-to-1 ratio because we have a 2-to-2 ratio.
We expect 1 to 2 to 1. Yeah.
2-1-1 ratio.
2, 1, 1.
Yeah.
Yes. Okay. Whatever. Yeah. So we expect a 2 to 1 to 1 or 1 to 1 ratio. This means we have 1 dominant SS. So 1 SS. We have 1 homozygote recessive, that's the SS, and we have 2 of the heterozygotes. Okay, does that make sense? So, what would be our numbers? So, observed, SS, the heterozygotes, that is observed. We have 25 SS, the heterozygotes. We have 12 of the homozygote recessives, and we have 3 of the homozygote dominant. Yeah? So these are our observed numbers. What are our expected numbers? Well, the expected numbers are still the same as we had before. So we said expected numbers are 10, 10, 10, and 10. These are the expected numbers if it is just random. So expected. How many for the heterozygotes do we have? 20. Exactly. How many for the homozygote recessive? 10. And for the homozygote dominant? 10. Okay, again, everything adds up to the total, to the grand total, as it should. Now, if you do the p-value for that, you will find that in this case, the p-value is 0.038 at an alpha of 0.05. What does this tell you? P is low. H0 must go. It means the observed data and the expected data show a statistically significant difference. So, difference here. Statistically significant difference between observed and expected data. Isn't that a bit strange? Our phenotype said, actually, it fits with this monohybrid cross, and now our genotype says there is something wrong. What could be wrong? Is there anything in the data set where you see there is something not right? Go on, use your genetic knowledge. Anton is groaning. Aha. The homozygote recessive is okay, but the homozygote dominant is very low. Yeah? So we've got only 3 here. Any idea why this could be? Any idea? Sorry?
Sexual selection.
Say again?
If they'd rather mate with smooth-skinned dragons.
But then that wouldn't explain the two that are heterozygous.
Uh-huh. Okay, good. What else could be the case?
You haven't taken a big enough sample?
We might not have taken a big enough sample. Very good. I like that, yeah? Very good. It could very well be that it's numbers. That's a numbers game. However, our p-value sort of says, actually, this is not just down to a numbers game. This is what the p-value actually indicates. This is not just due to not enough sample size. But in principle, you are right. If we increase the sample, we might get a more evenly balanced number. A biological explanation. What could be a biological explanation?
It could be something that kills the offspring for birth.
Absolutely. It could be that the combination of dominant scaly plus dominant scaly is lethal. Yeah? So there could be a biological explanation for that. It could be lethality or a very reduced fitness. Yeah? Does that make sense? So, when you look at data, the phenotype might be okay, but the genotype might throw up some problems. Does that make sense? Fantastic. So, for how do I get rid of these things? Yeah. Now, for these two examples that I showed you, we already had a sort of an idea, a preconception. We assumed that it is a monohybrid cross. We know that a monohybrid cross would have a phenotype of 3:1 and a genotype of 1:2:1 or 2:1:1. Yeah? So we had this preconception. And we could test our, in a way, scientific hypothesis. Do the observed data actually match the expected data? But what if we don't have this preconception, if we don't have this sort of idea what's going on here? I'll give you an example. From your assessed practical, yeah, it's going to bite you again. From your assessed practical, I got a little bit more data. So, for example, I checked out what is the distribution between gender in the morning and in the afternoon. And is there a certain gender preference or something weird going on in terms of who is allocated to which slot? And I found female, male, morning and afternoon. I found that we had 64 females in the morning and 78 females in the afternoon. We had 38 male in the morning and 44 male in the afternoon. Now again, we can do the margins. A total of 224. How many students did we have in the morning? We had 102 in the morning. How many do we have in the afternoon? Thank you. How many girls do we have? With girls, I mean females. Biologically female. 142. And how many true men? 52. What? 82, yes. Okay, so these are our margins, and if you do the count, they all add up to 224. Yes, we haven't missed out on anyone. Now here comes the problem. Is there anything fishy about it? Let's calculate the expected numbers. So that's observed. Expected numbers. Again, we do females, males, morning and afternoon. But how on earth do we calculate that? (224). Well, obviously, we can't change our margins. We know that we had 102 students in the afternoon, in the morning, and we had 122 students in the afternoon. We had 82 male, and we had, what was it, 142 girls. Yeah? And now we calculate from these numbers, from the margins, how many would we expect? And the way you do that is you multiply the relevant margin and divide by the grand total. So, for this one here, for the females in the morning, it would be 102 times 142, so that's this one here and this one here, divided by 224. For the males, you would do 102, that's this one here, times 82, divided by the grand total, 224. So when you do the expected numbers, you just do it with the figure out how many of these things are in the relevant square. So for the girls in the afternoon, what do we get? 122 times 142, 224. And for the boys in the afternoon, we get 122 times 82 divided by 224. Yeah? So again, what you do is, for this one here, for the first one, 102, that's the total margin here, times this total margin, divided by the grand total of 224. And you can do that for each square. And that gives you the numbers that are supposed, that are expected in here. So you have kindly calculated that. So we would get for this one 65. Is that right?
Yeah.
Yeah. For this one we would get, 37. We get 77 for this one here. And we get 45 for this one here. So I indicate it like that. So if we look at what we actually observe, we observe 64 girls in the morning, and our expected number would be 65. It's not too bad, huh? We expect 37 males in the morning, and actually we observed 38. So, not too far away. Likewise, 78 girls in the afternoon, 77 expected, 45 and 44. Yeah? It's not too big a difference. And again, what we now can do is we can do what is called a chi-square test. But this is no longer a goodness of fit test, because we don't have any preconception. We didn't say there must be a 3-to-1 distribution. What we used for this particular chi-square test is what is called a contingency table. Contingency table. And a contingency table is really something like that with our expected, because it has 2 rows, and we only count the rows that contain our actual data. We don't count the marginals. This is a 2-row two-column table. So this contingency table is also called a 2x2 table. And the rule for the contingency table for the expected numbers is, as I said, multiply the corresponding marginal numbers and divide by the grand total. That's where this contingency comes from. And in fact, there is a way to calculate a 2x2 table in this statistical program that I showed you, for which I'm going to send you the link, which is different from the goodness of fit. So you need to be clear, what am I going to calculate? Do I have any preconception? Is it monohybrid, or you can do it with a dihybrid? That would be a nice test question. Where you do these calculations. Do you have any preconception? Do you have any idea what it is? Or do you want to check out whether there is something weird going on? Now, I've done this, this calculation, and I got a p-value is 0.85 with an alpha of 0.05. What does this tell you? P is high, so H naught can stay. This means our null hypothesis says the data that we observe and the data that we expect are in line with each other. There is nothing fishy going on. Yeah? So there is no big surprise in the distribution, which isn't terribly shocking for me, because as far as I understand, this allocation, whether you are in the morning or in the afternoon, was done by the admin office. Is that right? Or did you choose it yourself? It was the admin office. So they basically don't give a damn who is in the morning and afternoon. And it basically tells me that it is random. There are no additional factors that contribute to this distribution. Yeah? Does it make sense? Are you happy with that? Yeah? Okay. So, I guess we are more or less coming to the end of these lovely statistics. Thank God for that. But you will get a lot of opportunity to practice these things, I promise you. However, before you bugger off and you think, you know, thank God we don't see him before Christmas, wrong. We still have a week, and on Thursday... Sorry?
Have we not got a lecture with you throughout this week, apart from Monday?
No. You have Thursday with me and next week.
That's fine.
Yeah? I hope that you say that it's fine. On Thursday, I want to do a little exercise with you. For this exercise, by the way, I have sign-in sheets for Thursday. Yes, I know. Life sucks. Yeah. On Thursday, I want you to bring along paper to write on, a pen with which you write on the paper, and a calculator. Yeah? Because we are starting a completely new chapter for which you have to, do something. Okay? See you on Thursday.